So I am Daniel Angles Alcázar. I am here at the CCA and also at the University of Connecticut. And I like galaxies. I like the multi-scale, multi-physics, multi-mass involved in galaxy evolution. As many as you know, in galaxy evolution, we need to know a little bit of many things. We need to know a little bit of cosmology because it's the background where galaxies are forming. Primordial density fluctuations grow over time and give rise to the galaxies that we observe today. So we need to understand a little bit of this cosmological background. We need to also learn about a little bit about star formation, how gas gets converted into stars. And also we need to learn to know a little bit about stellar evolution, how massive stars go off as supernovae and affect the environment, which is also very important for galaxy evolution. And we also need to know a little bit about massive black holes because they likely also play a key role in galaxy evolution. So we need to somehow find a way to combine many of these ingredients into simulations, models that can tell us how the overall galaxy formation process goes. So some of the specific questions that I'm more interested in are listed here. So I'm very interested in the coevolution of supermassive black holes and galaxies, how black hole feedback affect galaxies, how is that they end up correlating with each other the way they do. I am interested in galactic winds driven by stellar feedback processes and how winds eject mass from galaxies and how they interact with the circumgalactic medium of galaxies. And I'm interested more in general on large-scale gas flows in the context of galaxy evolution. And among other things, I would like to also list a very recent addition to my interests, which is I'm trying to learn as much as I can about cosmology and how we can use simulations, including all of these messy baryonic physics, to improve our understanding of and measurement of cosmological parameters. And so I'm bugging Paco and many other cosmologists around to learn about this. And so my main tool is cosmological hydrodynamic simulations. And I use this type of simulations to address these topics on different scales. So first of all, here to the left, this is an example of a large volume cosmological simulation. This is SIMBA, where we simulate a volume of about 100 megaparsecs with a resolution of about 1 kiloparsec. So these type of simulations are great in order to give you the large scale structure and try to do population statistics. But then I'm also interested in looking in more detail at the properties, internal properties of galaxies. And for this, we need to use cosmological zooming simulations, with much higher resolution, so that then the statistics is much worse, obviously, but then we can learn a lot about how the internal properties of galaxies evolve. And then, connected to my interest on supermassive black holes, we need to go to even higher resolution to then see how gas loses angular momentum and accretes onto the central supermassive black hole. And of course, I have a fantastic group of collaborators in all of these different projects. And I should say that if you resonate with any of these topics, please let me know, and I'll be very happy to chat about this. Okay, going forward. I'd like to show an example of these ultra-high resolution simulations where we increase the resolution dynamically close to the black hole in order to understand how black holes grow. And so the left panels here are showing how the gas distribution in the central 100 parsecs of a massive galaxy looks like in standard zooming simulations, which sort of looks like not very well defined, right? Fuzzy, not a lot of resolution. And then in the right panels here, you can see how things look like when we use this hyper refinement technique, where now we can see all sorts of substructure and then follow explicitly how gas falls down to very close to the black hole. And the panels here to the left and give you a sense of, again, the range of scales involved in this process, going from like megaparsec scales here in the top left, all the way down to the central 10 parsecs. Drummond is already up, so I'm gonna try and at least play one movie. Let's see if it works. Great. So this is a simulation of accretion-driven winds ejected from very close to the black hole, very fast winds that then interact with the surrounding ISM and propagate outwards, and also interact with the circumgalactic medium of the galaxy. And I am super low on time, and I'm going to stop here.
Beautiful. You finished with 0 seconds left, so let's thank Daniel. Okay. Hi. Thanks for being here. I'm going to talk about how I spent the last 8 years of my working life, which is on the Sloan Digital Sky Survey 4, which is right now entering its last year of observations. And the way this connects to computational astronomy, what's done here, is that one of the things I'm very interested in is the use of computational data analysis, data science techniques to not just analyze astronomical data, but to create the astronomical data. So that's a subtext here. So SDSS-4 is 3 surveys happening at 2 different observatories. I'll describe them in a second. But one thing I want to note is that we release all of our data on a roughly yearly timescale. Our next data release is in December. Our final data release will be in 2021. We do this on a regular cadence. The other thing I want to note is that this is a project that's funded almost entirely privately funded and funded actually majority by individual institutions. So this is the breakdown. 25% comes from our friends uptown at the Sloan Foundation, 5% from the DOE, but 70% comes from individual institutions. So if you look at this breakdown, our individual institutions are what is keeping us accelerating. It's our dark energy. Yeah. I'm competing with Blakesley. So the 3 projects, we have EBOS, which is a large-scale structure survey. So this connects very well with a lot of what people have been talking about. Looking at here today is the large-scale structure of the universe. EBOS finished in February. It finished basically the 20-year SDSS project of doing the largest galaxy redshift survey by a factor of 10 and measuring the expansion of the universe and the growth of structure from here all the way out to redshift 2.5. And so this is a really epical event that we actually completed this project or finished or ended or stopped redshift surveying after 20 years. There's 2 other programs. One is MANGA, which is an integral field spectroscopy survey of 10,000 nearby galaxies. This is continuing through the end of this year. There's a huge amount of information you get about each galaxy. You get a spatially resolved map spectroscopically. Here I'm just showing the angular momentum distribution shown in sort of the standard way galaxy people do. This connects very well to the next talk. You can also look at the ISM and the stellar populations, which connects very well to the previous talk. And finally, Apogee, which operates in bright time, is a stellar spectroscopy survey of stars in our Milky Way, studying galactic archaeology of all the components of the Milky Way, both from the south and from the north, both from the north and the south, and doing cartography of the Milky Way and stellar astrophysics. This is stolen from Jackie. This doesn't count as an extra slide because it already appeared. And so this is the apogee coverage on the sky shown on the dome. So we end at the end of next year, but we're being SDSS-5 is being prepared. This is being led by Juna Kohlmeyer. The Flatiron is part of SDSS-5. And from moving from the standard SDSS plates to using robots, we're going to be able to cover the whole sky. We're going to be able to do this in a time-resolved fashion. We're going to study stars in the Milky Way. We're going to study distant black holes. And in a sort of separate instrumentation project, we're going to do massive integral field spectroscopy covering thousands of square degrees of the Milky Way and neighboring galaxies. And this is looking at ionized gas and stellar populations. This is like cosmological zoom-in observations is what Juno likes to call it. And finally, in the last 15 seconds, the last thing I want to say is there will be an SDSS collaboration meeting here next June, here being at Flatiron. And so stay tuned for announcements about that. Thanks.
Sadly, no time for questions, but Michael's around, so you can ask him. All right, we got Shai up next.
Hi, good afternoon. So it's really a pleasure standing here in front of CCA and everyone else, especially on a day that's exactly 3 years since day one of CCA on September 6th, 2016, where we were 6 people over down the block at 22 West. So we've evolved a lot since then. And so this first slide, I want to give just a very broad overview of things that I'm interested in. So I love galaxies, and I work mostly with large-scale cosmological simulations, hydrodynamical simulations. So I was a member of the international small team that created the illustrious TNG simulations, which are 3 cosmological boxes out to from scales from 50 to 300 megaparsec on a side, which contain also not only dark matter, but also baryonic physics, star formation, black holes, and so on. And together are the largest suite of such hydrodynamical cosmological simulations with about a petabyte of data, and took about 200 million CPU hours to run. And they are a very rich data set that can be used for many, many projects. So the general science themes I'm interested in are galaxy growth, galaxy angular momentum, and how these things are connected, how angular momentum is accreted onto galaxies, and also how gas is accreted onto galaxies, and some aspects of galaxy structure. In particular, I want to mention 2 Columbia grad students I'm working with, Daniel De Filippis, who's working on the angular momentum of the CGM, and Bhavna Motwani, who was working on properties of star-forming regions and will now transition to working on the intra-cluster medium. And also a pre-doctoral student who will arrive on Monday and work with us for 5 months. And Chris Duckworth, who will work on acquisition of angular momentum in the cosmic web. So that's what I want to get into a little bit more detail on. So you saw in this movie the cosmic web, and these little all these lines show angular momentum of galaxies embedded in the cosmic web. So I want to show a few examples here of some interesting things. So what we see here are 4 galaxies. So we see on the left side the stellar component of the galaxy, and here the dark matter halo. So these are on different scales. This is in the very inner part of this. And in each such panel, we see the red line shows us the direction of the angular momentum is pointing at redshift 0. And the yellow line shows the direction of the angular momentum is pointing at in the initial conditions of the simulation for the same stuff that is shown here at redshift 0. Just looking at the same mass, what is the angular momentum at early times? And we see that for this galaxy, this can be very simple. They're all aligned, dark matter and stars, today and in the initial conditions. But we can have much more complicated, curious situations. So in this case, again, also for a disk galaxy, actually the halo and the galaxy are both keep their orientation between across cosmic time, but they are at 90 degrees between one another. In some cases, for elliptical galaxies, things can get even weirder. So there, you can see in this case the halo is consistent. So what we see is that at redshift 0, the halo and the galaxy are actually 180 degrees toward, from one another. But in the initial conditions, the yellow lines, they were aligned exactly in the same way. And here in this case, nothing aligns with nothing. So, okay. So I should finish very soon, but I want to just mention, how can this be, just one point, how can this be that even in the initial conditions, the stars or the baryons that will make stars and the dark matter are not aligned? And this is essentially because they're not formed exactly from the same thing. In other words, the initial patch of the baryons or of the stars, the initial patch of the dark matter are not exactly the same, as you can see here in 2 different colors. And Lastly and quickly, we can, so what I'm working on now is essentially plotting distributions of these various angles and trying to understand from this the origin of angular momentum of galaxies, and through this potentially trying to understand better why galaxies come in different morphologies. So stop here.
All right, let's take one question. David?
So there's been a lot of work where people compare galaxy alignments with large-scale fields, and most of the work is compared to simulations that are dark matter only.
Right. Mm-hmm.
This suggests that we have to revisit all of this.
Yes. Yes. So this will definitely, I have this in mind.
Yeah, it's
working
the
on this
large-scale
project.
structure stuff would be
Definitely.
great.
Yeah.
All right, next speaker. Let's thank Shai one more time, yeah? Here's Mehmet.
Hold up. All right, let me get set up. Thanks. Okay, hi. My name is Mehmet Alpaslan. I'm a postdoc at NYU. I too love galaxies. My background is largely in working with large galaxy surveys, so I cut my teeth on gamma and now work a little bit with SDSS. I'd like to tell you a little bit today about a recent result that we have been working on at NYU. This is mostly work with Jeremy Tinker. So we're interested in looking at what we can find out about galaxy groups and galaxy halos, or rather the halos that galaxies inhabit, by looking at their satellite galaxies. So we've introduced, or rather we're in the process of introducing this metric, which I actually believe has been looked at before, which we're dubbing LSAT, the satellite luminosity. And this can be derived quite simply by counting up the luminosity of all photometric sources within some distance, let's say 50 kiloparsecs of a central galaxy that you might identify with spectroscopy. In this case, our spectroscopic data comes from the main galaxy survey of SDSS, shown here in black, and we have deeper photometry going down to about 4 magnitudes deeper from the legacy surveys, which consists of this footprint that almost entirely overlaps with SDSS. So going into some more detail, we do some background subtraction on the satellite luminosity that we measure around the central galaxies. And so this remaining measure should be some proxy for the luminosity being emitted from the satellite population of galaxies. So what can LSAT tell us about groups and halos? And this is really, I think, something that's quite interesting and a result that I'm quite excited about. So these two plots are from some work that Jeremy's done, where here we're showing you the halo mass of a galaxy, the halo mass of the dark matter halo that a central galaxy is embedded within. And this is the satellite luminosity measured. The solid line comes from just essentially using a simulation where you have the true known grouping of objects, and so you can immediately infer which galaxies are in the satellite population. And the plotted lines come from simply using SDSS and using some sort of abundance matching formalism to estimate the mass of the halo. And you can see this extremely tight correlation with a slope of about 1.1, which essentially gives us a handle on the halo mass down to significantly lower halo masses that have been looked at before, simply by using this satellite luminosity. And on the right-hand side, you can see the same information, but recast as a function of the central galaxy stellar mass. Now, very importantly, and I think this is a reasonable question, we show that this really doesn't seem to be varying very greatly as a function of density. So this figure is showing you certain somewhat derived values for LSAT as a function of density, but you can see that it's a very minimal difference. And in fact, it doesn't really change as a function of central galaxy stellar mass in many different ways. So the question, therefore, is what other properties of central galaxies correlate really well with LSAT? And what we've shown using information theory, and this is a tool that I was very excited to use, so if you're interested in information theory, please come and speak to me. But we can show that the R-band absolute magnitude of a central galaxy is a better proxy for its total satellite luminosity than its stellar mass. What that therefore means is that you could, in principle, use the R-band luminosity of a central galaxy to get an estimate for its halo mass with a higher signal-to-noise ratio and down to lower halo masses than other techniques that are currently being used. And so if this is something you're interested in discussing, please come and talk to me, but we do this for the sample of SDSS galaxies that I talked about, and in some cases we also showed that certain other parameters, such as the size or the velocity dispersion of the galaxy, also give you a better handle on this LSAT parameter than stellar mass. Of course, this isn't all I do. There's a few other things that keep me up at night. I'm only going to focus on this one due to lack of time. I have somehow convinced Google to let me use their AutoML machine learning network for free for as long as I want. And if anybody is interested in helping me find out what amount of time is reasonable before they complain, come and let me know. This is a neural architecture search. As far as I'm aware, we don't really use this in the field very much, but it might be interesting to see how far we can get using proprietary code.
Some questions? All right, Catherine, you want to start us off?
So the satellite, is this working? The satellite. Okay, the satellite question. I know that there's a number, right? The number of satellites is stochastic. You're going to be okay, I'm making this up. You're going to be sensitive to the highest single velocity satellite. So when you make this plot, that error bar is the mean, right? But isn't there a huge range? So if you look at an individual galaxy, right? Yes.
You're absolutely right. There's a huge amount of noise on an individual on a per galaxy basis or per group basis. And so really these signals really come out when we're starting to sort of combine large data sets.
So sorry, when you're using this as an indicator, you don't mean per galaxy, you mean, yeah.
Of populations, yeah.
Okay.
Thank you for clarifying, though.
All right, let's thank Mehmet. Next up, our very own Katerina.
Hi everyone. So I'm Katerina, I'm a postdoc here. Galaxies are okay, but I do gravitational waves and data analysis for LIGO. So that's the obligatory gravitational wave plot from 150914, the first gravitational wave event detected with the data and the posterior for the reconstruction of the signal on top of it. I'm a member of LIGO, so I spend a lot of time since the third observing run started. I spent a lot of time on the incoming triggers. So whenever something like that happens, like the so-called binary neutron star that happened April 25th, I usually lose a little bit of sleep following up on it, but not nearly as much as the astronomers who have to follow up on this sky map. They are the real heroes here. Or the new cool kid on the block, the NSBH from August 14th, that has a high probability of being a neutron star black hole system. I also have a love-hate relationship with neutron stars within LIGO and gravitational waves. So from the gravitational wave signals, you can learn something about the composition of neutron stars from the tidal interactions as the neutron stars crash against each other. So today, with just one or maybe two signals observed, what we can do is we can take them and estimate the parameters of the system, like the masses of the neutron stars in 170817. I start mixing them. The binary neutron star, we can measure the masses, as well as the radii of the neutron star, how big the neutron stars that collide were. And from this one signal, we're between 10 and 12 kilometers. But I also like looking at what we can do in the future. Once you have populations of these sources, at design sensitivity, we expect to see dozens of these systems. So what you can learn from these systems about key properties of neutron stars and the properties of matter inside neutron stars. So here's an example of something that I worked on recently, where if you have a population of a lot of binary neutron stars, you can measure here an example measurement of the mass of neutron stars above which quark matter starts happening inside neutron star cores. So neutron stars are very dense. If the density exceeds certain limits inside their interiors, then quark matter can start leaking out of nuclei, and you have free-roaming nuclear quark matter inside neutron star cores. And if you have enough binary neutron star detections with gravitational wave signals, you can measure the mass of neutron stars at which this effect happens. And that could be useful to nuclear physicists studying the properties of this very, very dense matter. I also spent a lot of time working with something called BaseWave, which is a code that is essentially a sampler for transdimensional parameter spaces. That's parameter spaces whose dimensionality is not fixed, and it's a variable of the problem. And we usually use this kind of techniques and this algorithm for what we called unmodeled things. Basically, signals for which we don't have good models. So when you have a binary black hole, general relativity tells you to pretty good accuracy what the signal you expect looks like. But sometimes you don't know what the signals you expect will look like, and we can use these techniques to study them and either detect them or even estimate some key parameters that might help us figure out what those systems we see are. For example, imagine you get a burst of gravitational radiation that you have no idea where it comes from. You don't know what kind of models to analyze it. This is where you would apply something like that. So we have used this to do a bunch of things, such as study the emission and the properties of the emission, the gravitational wave emission after a neutron star merger. You have a final deformed, unstable neutron star remnant, and you can study the signal. So here are from an animation from simulations, where the red is the signal we inject, our simulated fake signal, and the green is the posterior reconstruction, how we'll reconstruct the signal as the signal gets louder and louder. So at first we don't reconstruct it, but as it gets louder, we pick up the signal. We can also use that, for example, to study what happens if black holes that collide are not really black holes as predicted by general relativity, but they have some sort of surface. Then what happens is they have, the emitted signal has this characteristic structure which keeps coming back at you called echoes. We also use it to model the noise in the detector. And also I spent a lot of time developing on this algorithm. And so the thing I wanted to put there in the fourth corner was what I was going to work on this summer, but didn't work. So I'm just going to say that what I really do most of the time is stare at plots like this and try to figure out why they don't work. Thank you.
Sadly, no time for questions. Let's move on. Chen, you go.
Hi everyone, I'm Chen Ding, a student from NYU. I work with Glenis Farrar and Noemi Globus, who's a postdoc at NYU MCCA, and I'm interested in understanding the origin of ultra-high energy cosmic ray anisotropy. By ultra-high energy, I mean it's on a scale of EeV, which is 10 to the 18 electron volts, which has much more energy than particles in Large Hadron Collider. In 2017, Pierre Auger Observatory detected the anisotropy above 8 EeV. The anisotropy can be described by a dipole of about 6.5% in amplitude, and the significance is 5.2 sigma. And it raises lots of interesting questions. Is like, where do the cosmic rays come from? Is it from a galactic source or an actual galactic source? Is it from one source, one or few sources, or like many sources? But the most interesting question for me is like, what information can be extracted from the information about this anisotropy? So we built a model, a physically motivated model, to understand the anisotropy. We consider the energy loss mechanisms, because as the cosmic rays travel in actual galactic medium, it could interact with CMB and lose its energy. And the cosmic rays diffuse in actual galactic magnetic field. From the information from the best fit parameters, we realized that the majority of the cosmic rays come from sources that is like within 300 megaparsec. So we need so we think that the cosmic rays aren't coming from one or two sources. They are coming from many like weak sources, and we assume that these sources follow the matter distribution, like the large-scale structure. Our model also considers that as the cosmic rays enter our galaxy, it gets deflected by the galactic magnetic field. And our model includes energy spectrum and composition. So this map is our model. The prediction is called the illumination map, which is the sky map of the flux of the cosmic rays illuminating the exterior of our galaxy. And it's mostly Virgo cluster because it's very close to us. And this is the map of this is the arrival map, is the sky map of what we observe on Earth. And this is compared with the observation, and this is our model. And our model is consistent with observation in terms of dipole amplitude and direction. And probably I don't have time to go over this. This is the energy dependence of dipole amplitude, and our model is consistent with observation. But I don't want to, given the success of our model, I don't want to lead you to think that we'll never be able to identify individual sources, or we'll never be able to find out what type of sources that produce such cosmic rays, because our model is not complete yet. For example, there are two hotspots above this 38 eeV energy range. There are two hotspots that's detected. One is the OJ hotspot, and the other is detected by another observatory called TA observatory. But in our model, we only have one hotspot here. So it's very possible that the TA hotspot is produced by some individual sources that is close to us, and we hope in the future we might be able to find out what this source is and what type of this source is. So thank you very much, and I would like to talk about it more about it after the session.
Questions, anyone? Well, all right. You'll have to think hard and come ask Chen later. All right. So our next speaker, we got Shirley Ho. Oh, let's thank Chen one more time.
Trying to time myself.
You got one right here.
Hello, everyone. I'm Shirley Ho, and I just realized I need to, yes. I just realized that it's been about a year that I've been in CCA, and two things fluctuated a lot since I got here. One is my weight. The second one is how people feel it when I give a talk about machine learning or deep learning applied to cosmology. The first one I think a lot of people realize was Flatiron 15 at this point. So when I first arrived, I lost about like 10 pounds just because I was walking New York City, going from California where you drive to losing all this weight. And I was post-baby. And then I slowly increased in weight over the last 6 months, and I started to realize I should start stopping this. So that's why I started stopping to eat lunch and stuff like that. That's why you don't see me just now. Second thing about machine learning and how people view it, over the last year or so, my talk had gone from everyone was like, what are you talking about? This is a black box trying to solve a black box like dark energy, but then using machine learning that nobody understands to try to solve dark energy. To, this is kind of interesting. So I'm going to try to see what's happening now with this crowd and let you, judge what's happened here. This is using, one of the many projects we do is to use deep learning as a fast approximate simulator. We need to come up with acronym better than fast, I guess. We went from analytical approximation of the universe, which is just gravity, very simple ones. And usually to go to a full n-body simulation, you take about 1.8 million seconds. So instead of doing that, we do it in 0.03 seconds with deep learning. I'll tell you a tiny bit more than that later. And then we did the next thing, which is using the Illustra simulations, which takes, I don't know how many million CPU hours, you tell me here. And if you consider that, Illustras, you only care about the positions of galaxies and the gas, density. Then we can produce it in 0.8 hours right now with machine learning. So these are papers run by students. Actually, some of them are master students. So let me tell you a little bit more details about those guys. So modeling the n-body dynamics with deep learning. The first part, the upper part, I'll try to use the stick just like here, because I'm kind of short. The analytical approximation, the percentage dark matter we use in the input and the training is about 30%. We train this neural net. It takes about 0.03 seconds to produce n-body simulations that's with, positions and velocities and the same latent parameters of cosmology. That's cool. What CEO He, who just graduated from here, and Yingli, who's arriving soon, have led is that they can also take the approximated, universe that has 10% or 50% dark matter, feed into the same network that was trained with dark matter percentage 30%, and output the correct full n-body simulations with the correct positions and velocity with the different latent parameters. So the machine learning people got really excited because they said, why would it work? Because the training set is different from the test set. So that's a mystery. We got published in something very famous because I think nobody understands what's happening, including us. So we're working on that. Any suggestions would be very useful. The next thing we did is try to model gas, galaxy, and something else. Here is to model the galaxies. We try to model what's happening in Illustris. So we went from using something very similar to the network you saw earlier, from dark matter to galaxy, and produce a galaxy 2-point functions. And for those who don't care, it's basically how galaxies correlate with each other. And you can do it with something called halo occupation distribution, this benchmark model usually. Don't look at the movie yet. And you can see that that's the benchmark, which is the orange line, which works really well at large scales. And I love it because this is k equals 1. This is really, really small scale further down. And it's very hard to model with anything we know analytically. But with machine learning, you can see that our method here, the blue line, is basically slightly different from the target until you hit the shot noise. That's for galaxies. And for the gas, here is the X1, so hydrogen. And you can see the 2-point correlation function here again. The XOD model is significantly under predicting how much power it is in, k equals to 1 or 10, actually 10, a few, and 100. While our model, we're able to predict basically very closely to what Illustris TNG is able to do, all in about 0.08 hours, which is basically 5 minutes. And something even crazier that we're doing right now these days is to try to use a network. Can you play the movie, or should I do something about this? Yes. To try to use a network to predict from the laminar state, which hopefully will show up soon like this, to the turbulent state, which will come up with all these little islands in there. So that's the next crazy project we're trying to do using machine learning. So if you are able to, do hydrodynamics, can you go from, for example, a plasma, like very simple laminar flow, to something so turbulent? I'll stop right here.
All right, no questions. It's going to be a session with no questions unless you guys keep it on time. All right, Colin, 4 minutes.
Challenge accepted. We'll see if I can do it. All right. Hi, everybody. See if this loads. All right. I'm Colin Hill. Many of you know me. I've been in the area for a while, but I've just started as an assistant professor in the physics department at Columbia, which I'm quite excited about. And I'm also splitting my time 50-50 here at Flatiron for the first 3 years as an ARS. So I work in cosmology. I spend a lot of my time working on various cosmic microwave background experiments, including these ones that I've listed here. I also work on some other things like gravitational lensing as well. I'm going to just show you some nice pictures of the Simons Observatory, which is one of these future experiments that you've probably heard people talking about, but I just want to emphasize that this is something that's actually happening. So I'll use the big stick as well. This is the cryostat for the Large Aperture Telescope, which is one of the 4 telescopes involved in the Simons Observatory. It's this one. We also have 3 small aperture telescopes focused just on primordial B modes. This thing is pretty big. It's something like a few meters across and can hold up to 60,000 detectors. And the whole thing is cryogenically cooled to just a fraction of a Kelvin, which is pretty amazing. This is the site where we're building SO. This is the ACT experiment right there. And we just had groundbreaking a few months ago. That's Jim Simons, David, Marilyn Simons as well. And we'll have first flight in 2021. So this is super exciting. So let me tell you a little bit about some of the science that we want to do with SO. So my interests kind of divide into 2 areas. First is doing extragalactic astrophysics with CMB, where we use the CMB as a backlight to essentially illuminate all the structure in the universe between our vantage point over here at redshift 0 and the surface of last scattering at redshift 1100. So this includes things like gravitational lensing of the CMB, the Sunyaev-Zeldovich effect, which is just the Compton scattering of CMB photons off of free electrons. So with current data from ACT and Planck, we have built the highest resolution and highest signal-to-noise map of the thermal Synev-Zeldovich effect to date, taking advantage of our multi-frequency data. So if you are interested in things like the properties of the gas in galaxies, this map is incredibly powerful for that. So you can just look by eye here, all these red spots in this map are the location of actual galaxy clusters in the sky. So this is pretty exciting. This is with Matt Madavacharil, who's at Perimeter, and Sigurd Ness, who's CCA as well. All right, and then my interests also intersect with doing fundamental physics with the CMB. So as you've probably heard, there is a problem with the Hubble constant, H0. It seems like the main activity at cosmology conferences these days is deciding what to call this problem. I'm calling it the H0 conundrum here, but feel free to offer up your favorite synonyms for what we should call it. So basically, the expansion rate of the universe inferred from measurements of the CMB or light element abundances plus BAO, baryon acoustic oscillations, and other data tends to come out lower than the expansion rate that is directly measured with the traditional distance ladder method, which presumably you've heard about. So there's been some interest in whether new physics might be responsible for this tension. It turns out that, well, so one might imagine introducing new physics in various places in the cosmological history. But one of the challenges is that if you introduce new physics in the early universe, where you might hope to alter the inference from here, that you tend to break observations of the CMB, which of course has been measured extremely well by many experiments. So it's been pointed out that there are ways to modify the dynamics of the universe prior to recombination in such a way that you can alter H0 without breaking the TT power spectrum, temperature power spectrum of the CMB. So this is an example of such a model. The blue curve that lies underneath the orange curve is a lambda CDM model fit to Planck data. And the orange curve is this exotic scalar field model that I can tell you more about if you're interested. But the key takeaway is just that the Hubble constant associated with the orange model is consistent with the late time measurements, whereas the blue one is not. So I think that that's pretty cool. However, no one has looked at how this affects large-scale structure measurements. So what we're working on right now with some collaborators at Brown is how the matter power spectrum changes in these models. And as you can see in this plot, the changes are on the level of 5 to 10%, including for modes that we can actually measure at high signal-to-noise. So these could put some interesting constraints on these scenarios. Okay, thank you. I did not succeed.
It's all right. We'll keep you anyway. Okay, David, finish us off strong. Maybe even on time.
Right. Okay, so what I want to talk about is using the cosmic microwave background and large-scale structure observations to constrain alternative gravity theories. And this is work done with Chris Pardo, who is defending his thesis on Monday. And the idea here is there's this remarkable agreement between the CMB temperature, power spectrum, what we see in large-scale structure. And the success of this model has been, I think, one of the great advances in cosmology. What does this tell us about alternative gravity theories? I've felt for a long time that this is telling us that we really can't have a successful alternative gravity theory, but it's been hard to articulate this clearly. And realize that one of the things we can do is look at CMB polarization. Now, CMB polarization is actually simpler to interpret than temperature. Temperature fluctuations are due to gravitational, a lot of terms could come into temperature. Polarization is simple. The polarization pattern we see in the microwave sky, this in Q and U modes, is nothing more than the gradient in the velocity fields. You're just seeing velocity fields projected on the sky. So when you look at the polarization maps from Planck, you're basically seeing what large-scale velocity fields look like at redshift of 1100. So we know what the velocities look like, and it's the velocities of the baryons. I have an alternative gravity theory, in which there's no dark matter. It's simple. Baryons are all there is. So then I can take this plus the continuity equation, and the EE power spectrum is the baryon power spectrum at redshift 1100, up to some constants. So we know what the baryon power spectrum looks like at redshift of 1100. We also see what the galaxy distribution looks like at redshift 0.3. Now, one of the things that confuses people is you're used to seeing plots of baryon acoustic oscillations. Those are always plotted when you divide out a smooth function to emphasize the wiggles. This is what the Sloan power spectrum looks like. And the reason that people like Michael Blanton and Shirley Ho worked really hard to get big surveys is the ripples on top of this spectrum are tiny. They are suppressed by a megabaryon over a mega dark matter squared. So they're suppressed by factor 25. Now, that's the way in standard theory we go from here to here. If you want to have an alternative gravity theory, it has to get from the blue curve to the black curve. And everything is in the linear regime then. So this tells us what the Green's function has to look like for the theory. And you can see gravity has to be positive here, negative here, positive here, negative here, positive here. Any alternative theory has to have this behavior to go linearly from here to here. And this doesn't look like Mond. This doesn't look like anything anyone's proposed. And it's pretty hard to come up with any physics that will have that gravity changing sign as a function of scale to cancel BAL. The alternative you might ask about is what if you had nonlinear theory? If you had nonlinear theories, we would nonlinearly couple the modes. You'd have a non-trivial 3-point function in any nonlinear theory. So I think we have very good constraints on non-Gaussianity as a function of redshift. We can rule out nonlinear theory. So for me, this means the combination of these observations basically says you cannot have an alternative gravity theory explain dark matter and be consistent with our observations of the microwave background and large-scale structure. So that's the constraints we've been able to put on, and I've been able to do it within my time.
That's why he gets the big bucks. Okay. Any questions for David? Emil.
That's correct. You can do something where you have some dark matter, but then, this is the stuff that, people like Stacy McGaw and Modi Milgram have been saying, you haven't found dark matter in the lab, therefore, it doesn't exist. Now, I would say that we have seen dark matter in the microwave sky.
Any last question?
That's not, that also must fit large-scale structure, but that tends to change the way things evolve overall. And as long as you have dark matter, you can explain, really the key thing is the suppression of these baryon wiggles, right? So
I was wondering whether this kind of approach could be extended to the.
Well, we know that you've got to fit large-scale structure, but you can't do the K dependence in the same way for a dark energy theory. So, did I get one more question?
All right.
Well, you need them to operate on the scale of 100 megaparsecs. So, and you need them to do it in a way that maintains the microwave background's remarkably Gaussian. So the process has to be basically linear to maintain the Gaussian nature of the microwave background fluctuations. So, you can't write a no-go theorem for all alternative theories, but this does give a very strong constraint, I believe, on alternative models.